Good morning, my YouTube viewers. It is Crystal here, and I'm going to do a code review for you. This particular code review, we're going to compare a sequential API to a functional API in Keras TensorFlow, and we're going to use the California house prices to do that. And the reason why we're going to use the California house prices is because that comes with Google Colab. So if you come over here to Google Colab, it says connecting to runtime. I got a message saying if you come over here to sample data, then it says California housing. So there's your California house prices data set, so you don't have to even do anything to find a data set. It's in the Google Colab data set, and we're using Google Colab to write this program. So that's good. So we've used Google Colab to write the program on California house prices. The only disadvantage that I can see of Google Colab is the fact that it doesn't have a very good undo function. So because of that, you have to be very careful not to accidentally overwrite or delete valuable code. If that does happen, you should be able to go into the save history and retrieve the code, but you don't always get to retrieve it, so you do need to be careful when you're thinking about overwriting code or deleting code. So after we created this program, what we're going to do is we're going to import the libraries that we're going to need. We're going to import pandas as PD, which that creates data frames in series, and it also processes data. We're going to import NumPy as NP, and that creates NumPy arrays and performs numerical computations. We're going to import matplotlib.pyplot as PLT, that visualizes your data, and we're going to import Seaborn as SNS, and that visualizes your data statistically. After we've imported the libraries that we're going to need to run the program, what we're going to do is we're going to use pandas to read the data sets that are provided with Google Colab. So you've got a train and a test CSV file. So pandas is going to read these in and convert them to data frames. And we've got a train and a test data frame. So you can see train right here. It's got a longitude, a latitude, a housing median, a total rooms, total bedrooms, population, households, median income, median house value. And the median house value is your target. And your test file is the same. So now what we're going to do is we're going to create a new data frame called combi, and what we're going to do is we're going to append test to train, and that's going to be one long data frame that contains both train and test rows of data in it. Now we're going to analyze the data frame. So you check your train, and so your train is your all floats, so that's good because there's not any object columns, and because there's not any object columns, you don't have anything to impute. We're going to check for null values. There's not any null values, so that's good. So that means there's not anything to impute. And what I will do is this says train info. Probably best to say combi info. Now we're going to analyze the target. We're going to use a Seaborn displot to do that, and you can see over here on the $500,000 range, you've got a lot of houses there. We do a value counts, and so you can see that on the value counts, we've got quite a few values that appear only once, and those values that appear only once, we're going to need to delete those values because it doesn't add anything to the reading. If it doesn't add anything to the prediction to have those values that appear only once in there. So we're just going to delete all of the values, delete all the rows where the median house value is only once, and we're going to use this code here. So now you can see what it looks like again, and you can see that it's a little bit more spread out, although we still have a lot of 500,000s. We created a heat map, and when we create the heat map, we're going to use Seaborn to do that. And when we create the heat map, you can see the total rooms, the total bedrooms, the population, and the households are correlated. Excuse me. And then in addition to that, you can see that the median income and the median house value are correlated as well. So obviously, the higher the income, the higher the house value. So here's the correlation. If you want to see how all of the columns are correlated to each other, you can see that. If it's a negative value, it has a negative correlation. If it's a positive value, it has a positive correlation. So now we're going to remove columns that have a high correlation, but I decided not to do that. I decided to keep the code in there, but I decided not to do that because I decided that there's not that many columns of data, not that many features, so we may as well just leave it in there. So I left the code in there, but I didn't remove any columns that had a high correlation. So now we created a scatter plot for median income, and so you can see that really the higher the income, the higher the median house value. So you can see that. Excuse me, I sneezed a little while ago. So now what we're going to do is we create a box plot for median house age. So you can see that tells you the age of the house and then what the value is. What's interesting is if it's 52 years old, it seems that was the highest. So that was interesting. Now we're going to create a map of the latitude and the longitude. And so you can see we're going to do a joint plot for that. And so that's your latitude and your longitude. Now what we're going to do is we're going to define our X and our Y values. So X is the combi drop median house values, axis equals 1, and Y is combi dot median house values. And there's another way that you could do that I found out since I wrote this program. Y could be combi dot pop median house values, and then if you do X, then you say combi, and then that will have taken median house values out of it. So that's just another way that you can do it, because there's lots of different ways that you can do things in Python. So now we're going to check our feature length equals len x.columns. So your feature length is going to be 8. Now we're going to split X for training and validation. We're going to use sklearn's train test split to do that. So you're going to have X train, X val, Y train, Y val. So we split it. So now what we're going to do is we're going to use Keras TensorFlow. And so we import all of the libraries for TensorFlow, and we also print the version of TensorFlow that we're on, and we're on version 2.12. So now the first thing we want to do is we want to use TensorFlow to normalize the data. Normalizer equals normalization, axis equals -1. And then normalizer.adapt, NP array X train. And then print normalizer.mean.numpy, so you can see the normalized data. So now what we're going to do is we're going to check the normalization for the first row of data. So the first row of data, you can see what it's like when it's not normalized, and then you can see what it's like when it is normalized. Now what we're going to do is we're going to define a sequential model. So model equals sequential, model.add normalizer, Model.add.dense is 30. Input dim equals feature len, activation equals ReLU. Model.add.dense 30, activation equals ReLU. Model.add.dense 15 is ReLU, and model.add.dense 1. And then so we print off a summary of the model so you can see that. Now we're going to compile the model with the loss is going to be mean squared error, the optimizer is going to be atom, and the matrix is going to be mean absolute error. So we're going to set it up for early stopping equals early stopping, monitor equals valve loss, mode is min, patience equals 25, verbose equals 1, MC is your model checkpoint, so it's going to be best model.h5, monitor equals valve loss, mode equals min, save best only equals true, and now we're going to train the data. So history equals model.fit, x train, y train, epochs equals 300, and I will say that I could have made it more epochs because it still didn't do early stopping. So I could have made it 400 epochs. I don't know how many epochs I would have needed to make it, but validation data is x val, y val. Batch size, I made that 64. Callbacks equals early stopping MC. So we can see here that we got all the way down to 300, or all the way up to 300, and we still didn't have early stopping. So I could have made it more epochs if I had wanted to. Probably should have, shouldn't I? But, you know, the more epochs you have, the longer the training time is, and so I just kept it at 300 epochs, but you need to have it as many epochs as you can get, so before it stops. It's supposed to do early stopping, which it didn't do early stopping in this instance. So now what we do is we plot a graph of loss, MAE, val loss, and val MAE. So the loss and the val loss are the same, and the MAE and the val MAE are the same. So we make predictions on it, and then we check our RMSC at 61523, and really what we should have done is we should have done YPRED to actually show the predictions, but we didn't do that. So now what we do is we check our RMSC, which is 61523. We check we do a plot of the actual values against the predicted values, so you can see that. And then we compare the actual values against the predicted values. So I guess we probably don't need to do the YPRED, because over here I created a data frame where you can compare the actual values against the predicted values. But what I will say here probably should be a float. I made it an int, but it should be a float, really. So that was what we did for our sequential model. So now what we're going to do is we're going to define a functional model. And the thing is that when you define the functional model, what shall we say? It doesn't say functional. You know how on the sequential model it says sequential, and the functional model it doesn't say functional. I guess if it doesn't say sequential, then you're going to just have to assume that it's functional, because Keras only has two model APIs, and they're sequential and functional. So this is your functional model, which input equals input shape equals x train dot shape 1. So that is to say, and we could have done, instead of saying X train shape 1, we could have said feature len right here. Feature len. So rather than saying X train shape 1, we could have said feature len, which is probably what we should have done. And then Normalize equals normalize our input, so we're going to normalize the data. Hidden 1 equals 30. Activation, read loop on normalize, so it acts like a function. Hidden 2 is dense 30. Activation, read loop, hidden 1, so it acts like a function. And concat is concatenate input and hidden 2. So input is going to go directly to hidden 2. Output equals dense 1 concat. Model 1 equals model. Inputs equals input 1. Outputs equals output. And then model 1 summary. And this is what you get for the model 1 summary. And then so model 1, we do this model 1 exactly the same way that we did previously. We compile it, and then we set up early stopping, and we set up MC, and then we set up history. 1 equals model 1 dot fit, X train, Y train, epochs equals 300, validation data equals X val, Y val, batch size equals 64, callbacks equals early stopping MC. And you can see it went all the way up to 300 and we didn't have any early stopping. So I could set it up to 400 really. I can set this up to 400 and see if it does early stopping when I set it up to 400. And then what we do is we evaluate the model, and we had an MAE of 44326. And then what we do is we create another graph, and you can see here that the loss is the same as the val loss, and the MAE is the same as the val MAE. We make predictions on X val, and our RMSC is 62537, so the RMSC is just slightly more than it was using the sequential model, so that means it didn't work as well. And now what we do is we plot out the actual values against the predicted values. And here you can see we've got our actual values and our predicted values. So what I wanted to do was I just wanted to compare this to sklearn. So I standardized the data in a similar way that I normalized it with Keras TensorFlow to make sure that we were on the same playing field. So x1 equals x minus x mean over standard deviation of x. Then we split the data, so you had x train, x val, y train, y val, using train test split, and using x1, y, test size equals 0.1 and random state equals 42, and then we put it on linear regression. We had 63% accuracy when we used linear regression. We had a 66207 RMSC on linear regression, so that means it was lower than the sequential and it was worse, it was higher than the sequential and the functional API. And this is what it looks like, the predicted values against the actual values. And then here what we did was we created a data frame that shows you your actual values and your predicted values. So in this particular program that I wrote, the sequential model worked the best, the functional model worked the second best, and the linear regression worked the third best. So that's what I wanted to do. I wanted to do an exercise on functional models. So that's what we did in this particular code review. So you can see how you do a functional model. I've never worked on a functional model before, which is why I wanted to do a code review. And I hope you like it. I hope you get some insight into how to use a functional model as well as a sequential model. So I'm going to go ahead and close this code review because we've been talking for almost 20 minutes. I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you would like to be notified whenever I make a video, please tap onto the bell button next to the subscribe button. And thank you for watching my code review. I look forward to making more code reviews for you in the future.